Hey everyone, in this video I'm going through the Head Start program for 2023 going into 2024. Now these solutions were done last year, so on your booklet you have 2024, even though it's 2023, so I guess we can get away with it. Anyway, this video is going to focus on the first topic. So if we just scroll down to the contents, I'm sorry, PDFs are really hard to scroll on, but anyway, the overview of what is contained in methods we're going to go through in class, but the coordinate geometry and the quadratic equations of parabolas, all of that I'm going to do by video just for the benefit of those who may be absent, or I know I'm also missing quite a few lessons, so I'm sorry in advance. But hopefully these videos do help you. So I'm going to keep this one, I'm not going to cover everything because that'll take forever, but just to complement the solution. So you do have these solutions on Google Classroom, but just talking about them sometimes a little bit more helpful. Okay, so in the very first part, we're looking at solving linear equations and literal equations. So you'll see A, B, C, and D linear equations. So just solving for X. All right, stuff that you've done for quite a long time, probably a little bit harder than what you started off with when you started solving equations in year 7, but you have the skills to do it. So a bit of fractions in there, just make sure you have the same denominators. You do need to be confident with fractions in methods. So the 2023 exam had a lot of fractions in it. So make sure you're confident with dealing with fractions. And then questions E to N, we've got literal equations. So you'll see the main difference between E to N and A to D is that the literal equations have pronumerals instead of numbers. So it does add an element of difficulty, but the reason for doing so is it kind of adds an element of understanding how to solve equations or what is happening with equations, or the graphs of the equations, what happens when you change values, etc. So I'm not going to focus on any questions in A to D, but doing some literal equations, and I've already got the solutions here just because it saves a bit of time. I'm not pausing and thinking and blah blah blah, and it just allows you to work through the video a bit quicker and pause when you want to, I guess. Okay, did I do a question? Maybe I did. Okay. Just having a quick look at E. So I can't highlight here, all I can do is write in red, unfortunately. But with question E, always look at factorizing, and we want to take out X as a common factor. So you can see here we've got the two X terms together on the left-hand side. And that means you can just take X out as a common factor. So even if there was another factor that was common, because X is what you want, what you're solving for, taking that out as a common factor is definitely helpful. All right, and then solving that does not look difficult. All right, question, sorry about that. Question F. So you can, what happened here? So we're solving for X. You can cross multiply. So you can see I did that in 2 steps. So cross multiplying just means if I multiplied by X, both sides by X, gets rid of that X. And if I multiply both sides by X plus A, sorry, very sloppy writing here, they cancel out. So, which is the same as just saying cross multiply. So we end up with this expression. So we don't have any fractions anymore. And then just like the previous question, putting your X terms on the same side. So we've got X minus BX and then taking out the X as a common factor. Don't make the mistake of assuming that this B cancels out with this B. You can't do that when you're adding or subtracting terms. So you can see there we've got 1 minus B on what we did until I kind of drew all over it. Yeah, you can't cancel out like that. So please don't make the mistake of just thinking, oh, there's a B on the top, there's a B on the bottom, let's cancel those B's out. Doesn't work that way, and I don't like that being incorrect. So I'm just going to put it back to how it should be. All right, question G, again, we can do some cross multiplying. So you can see that's happened in this second line. And then we bring the x terms together. So you can see here we've got bx minus 2bx. And then obviously b is also a common factor, but because we're solving for x, we only want to take the x out. All right, we can leave that b inside the bracket. And then dividing, oh well, obviously this simplifies to negative b, but then dividing both sides by negative b. Now here's another example of, oh, you could have cancelled out those b's. I don't know why I did do that. So that b and that b and that b actually cancel out, and the negatives cancel out with the negative down the bottom. And then we're just left with 2a plus a, and we can get 3a, but you can see I've brought out the common factor, probably just to show, okay, that cancels out with the b and that negative, still ending up with 3a. Now, you can do, just going on a little tangent here, you can do these questions on your calculator. So here is one I prepared earlier. All right, just be careful. So you can see I've used solved. If you have two letters together or a number and a letter together, just make sure you whack a times in between. So you can see my 2b, just put a times in. And when you're, so x, y, and z are obviously on your keyboard. Oh, sorry, down here, x, y, and z. But if you wanted to put in another letter, just use the A, B, C, not the var, and you can see the main difference. You got fancy letters there or just normal A, B, C. All right, so just the B and the A I've put in there, and then you can solve for X. So if you need to check your any of your answers, you can just whack it in to your calculator, use solve, or I'm a huge fan of Photomath, just scan that puppy and it'll come out with the answer. All right, let's keep going. So question H, excuse me. All right, so we've got two different denominators and we can't do any cross multiplying here because these lovely plus signs. All right, we can't do that. Can't do that yet. But you can see in this second row, I've just made everything have the same denominator, mn. All right, so to do that, remember, whatever you do to the top, you got to do to the bottom. So this first term, which was x over m, and I might just get rid of those circles so we can see, just multiplying it by n over n. So then we're left with xn over mn, and so on. Just with, sorry, I might just keep going actually, instead of saying so on, just the next one. So we've got n. So if I want mn on the denominator, I'm basically multiplying it by mn over mn. This does not look like an m, and that doesn't look like an o. Sorry guys, let's just go back and do that again. Times mn over mn. So the n, that's times n is where the n squared comes from, and then on the right hand side, pretty much the same deal. All right, bringing your x's over to the same side. So you can see there I've got xn minus xm, bringing x out as a common factor, and then it's pretty much the same as before. What did we do here? Okay, so at this stage here, you're probably thinking, well, the n minus, I've got n minus m here and m minus n here. Now, obviously, they're not the same, all right, because m minus n is not the same as n minus m. But I can just change this one to a numerator to be n minus m if I was to multiply it by a negative. Okay, so that's why we end up with that negative there. So just changing this bracket here to be n minus n then allows me to cross them out, and I'm just left with negative m times n, what x equals. Okay. Let's see, any of these tricky. Oh, actually, I'm looking at, no, I was wondering if that was going to be a difference of perfect squares, because we've got difference of perfect squares here, but that's not going to allow us to cancel anything out. So do always be on the lookout for perfect squares. So a squared minus b squared is a perfect square. So I sort of this in my head. So that's the same as a plus b, a minus b. But there's no point in doing that because it doesn't really cancel out with anything on the denominator. So it can stay as a squared minus b squared over 2ab. As I'm talking, I'm thinking, I hope you're pausing after each question because I'm going mighty quickly, not probably allowing you enough time to work through them. So pausing is great. All right, what do we got for the next one? So where's our x? We got an x here and we've got the x here. So expanding always helps, especially, well, yeah, definitely if that x is inside your bracket or even if it's outside your bracket. It just means you're then getting all your x terms. So you can see we've now got this p squared x term, this pq rx term, and q squared x term. So we can bring everything together like I've done here, and then you can take out the x as a common factor. Then we're left with, and this is where it gets fancy pants, q squared plus p squared plus 2pq. So that is actually a perfect square. And that's where your understanding of quadratics comes in. And things like this, you might think, oh my gosh, how am I supposed to remember that? You just get exposed to questions, well, hopefully you get exposed to enough questions where you can pick it up. And this is where it gets tricky because if, say, Q was X or whatever, and P was a number, you could easily work it out, all right, as a monic quadratic, but it's not. So you've just got to be familiar with things like difference of perfect squares, which I talked about before, and here we've got a perfect square. So what I mean by perfect square, and let's just do one with x. So let's say I had x plus 2 squared. So that's the same as x plus 2 times x plus 2. So we get x squared plus 2x plus 2x plus 2 squared. So this x squared and this 2 squared are effectively in our quadratic up here, our q squared and our p squared. All right, it just happens that I've used x and 2. And then the 2pq is, we've got the 2 times x. All right, so that's where the 2pq comes from. And then the p squared minus q squared on this side, that is the difference of perfect squares. So what I said in the previous question, that becomes p plus q, p minus q. So probably the first difficult question we're coming across here. Now the purpose of factorizing these instead of leaving them in their expanded form is so that we can cancel out. So you can see if we didn't do that, we would be left with all these, we could probably cross out those p squareds actually, now that I'm thinking. No, I can't, because the x is multiplying there. Sorry, I'm just thinking to myself. Okay, so perfect squares and difference of perfect squares just enable us to simplify it to this, as opposed to having all those terms. So things you need to look out for. A question like this would be very good to put into your bound book. Now I know you can't take your bound book into your tech-free exam, where you might have a question like this to do without a calculator, but you can have your books in your sack. So I would definitely put a question like this in your bound book. Don't go putting heaps of stuff in your bound book. When you come across a nice question like that, put it in. All right, here, what have we got? So bringing the x's over to both sides, and you can see they have different denominators. So we give them the same denominator, which is AB. And then we can multiply by AB. So, well, I kind of feel like I've skipped a step. So we've got BX plus AX over AB. So the whole point of making the denominators the same is so we can have them over one denominator, and then we multiply both sides by AB. All right, so that cancels out, and that's why we're left with this. Taking the x out as a common factor again, like we did before, and then we're left with 3ab over b minus a. All right, I kind of feel like we've done most of them. Look at question N. Isn't that just scary? This is where you really get tested in your ability to do algebra. It is like, oh my God. And the difficulty comes in because we have different denominators here. So you can see I've made them the same denominator, but it's just an annoying same denominator, but you can do that. And then I cross multiplied. So if you're wondering what happened on this line, just multiplying them, it looks like, and then expanding, and then just simplifying as much as possible. So, you know, looking at your like terms, looking at what can be cancelled out, and just look at what it ends up as, negative 5a on 3, like from all that. And I just think sometimes when you do a question like this and you get to the very end and you get it right, it's just so rewarding. Okay, so have a go at doing this question. I basically gave you a few hints, but yeah, not beyond your ability. So if you're in methods, you should be able to do this. You've learned how to factorize, you've learned how to expand, you've learned how to deal with fractions. All right, it is not beyond what you're capable of. Just take your time and think about it, and just be careful with your negatives. Be careful with when multiplying. Be careful when expanding your brackets. Can't tell you how many times I see this and students write x squared plus 4. Guys, it's not the same thing. All right, so just be careful with your expanding. I'm going to get rid of that because I know it's wrong. Okay, so that is the first part, and I'm going to go through simultaneous equations as well in this video. So if you want to finish those questions first, you know what to do, just pause. All right, I love these sorts of questions. Sounds very nerdy of me. So simultaneous equations. So you should have done this since year 10. There are 3 types of simultaneous solutions to simultaneous equations, I should say. And they're these 3 cases here. So, and they've only drawn 2. Why do we? Okay, I think the third one hasn't been done because it's actually the same line. So what we've got, first of all, you can see these are parallel lines. So when your lines are parallel, you have the same gradient. All right, but they have a different y-intercept. All right, so same gradient, but different y-intercept. Here we've got an intersection, so we have a solution. So also this one, we have no solution. So this one here, we have a unique solution. So the word unique meaning one solution. And they basically cross over. So different gradients. They could have the same y-intercept because that the intersection point could be on the y-intercept, but different gradients, immediately they have a solution. All right, so when we're looking at what type of solution we have, we always look at the gradient first. All right, so if they're same gradient, then we know they're either parallel, so no solutions, so distinct parallel lines, or the third type is infinitely many solutions. So infinitely many solutions just means you have the same line. So there's one line, and I'm not going to draw exactly the same line because that's pretty impossible. But basically the 2 lines are on top of each other. And then an example of that could be the line 2x plus 2y equals 5. And anything that is a multiple of that, so 4x plus 4y equals 10, is actually the same line, because if I was to factorize this or divide everything by 2, I would end up with this same line. Okay, so same lines, they have the same gradient, and because they're the same line, they actually have the same y-intercept. All right, these notes you do need to put into your bound book because this sort of stuff comes up all the time. All right, so to test whether, well, what type of solution it is, so it could be no solution, one solution, or infinitely many solutions. So I've got 3 questions here, and I think there's one of each. Oh, and then I've got matrices. So yeah, don't worry about matrices. It's no longer on the course. So I'm going to show you another way as well that I only really learnt this year, but it makes sense because I've always used this first way. And this first way is similar to the matrices way, but don't worry too much about the matrix way. All right, so what we do when we're looking at the type of solution is we look at the coefficients of x and the coefficients of y. So you'll notice what I've done here, and I might just write it, is I've taken the coefficients of x. So in the first one it's 3, in the second one it's 3. And are they equal to the coefficients, or the ratio of coefficients of y? So effectively I've got 1 and -1. Are they equal? No. All right, so if they're not equal, then you have a unique solution. And I've written there one solution, so same thing. All right, the other way you can do it, and I might write it up here. Oops. Sorry, I was trying to touch my screen to scroll up, but it doesn't like that. You can rearrange your equations. So we've got 3x plus 2y equals 6. So we're just rearranging it to get it in the form y equals mx plus c. So 6 on 2 is 3. Okay, so our gradient is -3 on 2, and the y-intercept is 3 for that first one. Then the second one, second equation, so I'm just going to rearrange that. Plus 12. Our gradient is 3 on 2, so this one's -3 on 2, this is 3 on 2, so different gradients. Okay, so you can rearrange it in, if you want, into the form y equals mx plus c. Sometimes, but very rarely, that method that I've just done is the better method, but this is so much quicker. So much quicker. You're just looking at those coefficients. And the reason you're looking at those coefficients, so let's have a look. Oh yeah, sorry. Just got a little bit. Yeah, so when they're not equal, you have a unique solution, sorry. So let's have a look at the next one. B, sorry, I'm just thinking as I'm writing and talking. So the coefficients, well, this coefficient of x is 1. So the coefficients here, 1 over 2. And then we've got 2 over 4. So we know straight away that 2 over 4 is a half. So therefore, it's not going to be a unique solution. All right, it's not a unique solution, but then we have to decide, okay, is it case number 2 where we've got parallel lines, or is it case number 3 where we've got the same equation? Now this one you can look at and see that it's going to be the same equation, but to test, then we go, all right, let's check whether the ratio of the constants is also a half. And it is. So therefore it's the same equation. So basically if we look at these two equations up here, and I might just delete all this so we can go back up, and it's written there in pencil, so you don't need it written there. So to go from x to 2x, I multiplied by 2. To go from 2y to 4y, I multiplied by 2. To go from 6 to 12, I multiplied by 2. So it's the same line. We're just basically increasing it by a factor of 2, but it ends up being the same line, okay? Because each term in that equation is multiplied by the same factor. All right, whereas in the previous question, going from 3 to 3, we're multiplying it by 1. Going from 2 to negative 2, we're multiplying it by negative 1. And then going from 6 to 12, we don't even need to test that because once you know that whether the gradient's the same or not, we don't need to look at the constants. All right, and then the last one, you can see these are the same. All right, so then we go, all right, we say, okay, it's not a unique solution. It's either infinite solutions or no solutions. And once you've decided that there's no unique solution, then you say, all right, 3 over 12. So 3 over 12 is not the same as a half, so it's no solution. So they're parallel lines, they're not the same line. So if we go back up to the top, it's this case here where you've got parallel lines. All right, and then there's just another question there, which I probably should do because it's a bit tricky, and then we'll end the video here. Okay, so we've got this time a coefficient of x is m, and the coefficient in the second equation for y is negative 2 minus m. Okay, so you can see I'm still dealing with the same method. All right, I've got m over 4 is equal to 2 over negative 2 minus m. This part here, you don't need to do until later. If I was to do this again, I probably wouldn't write that, but you can see in this step here, I just go on to deal with the first two, because the first two just tell me whether it's a unique solution or not a unique solution. And then this last one tells me whether it's the same line or not. However, in this question, we're looking for, first of all, no solutions and infinitely many solutions. So I'm going to go a bit slower with this one because I feel like I'm going too quickly. So you probably, hopefully understand what I've done first of all. The coefficients of our x, so m over 4, is equal to negative 2 over 2 minus m. Then this is where your practice of literal equations really comes in handy. Okay, we end up with m squared minus 2m minus 8. So here we've got basically a quadratic expression. Even though we're used to seeing x being used, it's okay that it's m, and it's usually m in questions like this. So two numbers that multiply to give me the negative 8, so that's where the negative 4 and the 2 come from, and add to give you negative 2, so negative 2 and 2. So hopefully you can factorize that quadratic quite confidently. Because we're letting it equal 0, that means either m minus 4 equals 0 or m plus 2 equals 0. So I end up with m equals 4 and m equals negative 2. And often with these types of questions, you do have two types of solutions. And when you think about it, one, not in every case, but one usually represents the case where you've got parallel lines, and the other one represents the case where you've got the same line. So what you need to do is then use this 8 over 2m. All right, so I'm going to substitute in m equals 4, first of all. So just testing its ratio with m over 4 equals 8 over 2m. So I'm using this m over 4 because remember, if the ratios are equal for all three, then they're the same line. All right, so when I substitute 4 in, I get 4 over 4 and 8 over 4. Sorry, 8 over 8. So when m equals 4, we have infinite solutions. It's the same line. I could have substituted this 4 into this one here, and I would have also got 1. So 2 over negative 2 minus 4, so it gives you 2 over 2, which is 1. So I just chose this m over 4 because it's easier to substitute in a value. Just slightly, but it doesn't matter. You could have used this one here as well. All right, so I know when m equals 4, I have infinite solutions. So let's see what happens when m equals negative 2. So substituting that in again, I got negative 2 over 4. And why didn't I substitute in? So this should be, sorry, that should be an 8. is not the same as 8 over 4. So when m equals -2, we have no solutions. They're parallel lines. Part B, so going back up to the question, solve the equations in terms of m for suitable values of m. So basically, what I've got here I'm just wondering what that, okay, so we're solving for x and y, not solving for m. Okay, so m, to have a solution, m can be absolutely any number except for the m equals 4 and the m equals -2. Because when m equals 4, we have infinite solutions. Okay, we're not having the same, we've got the same line basically. When m equals -2, we have no solutions. There's parallel lines, they're never going to cross. So m is an element of any real number excluding, so this dash means excluding, the subset of -2 and 4. All right, so using these curly brackets, we're not doing a range of values. If we were using a range of values, we would use curved brackets, but these squiggly brackets just means we're excluding -2 and 4. All right, so solving for x and y. So if we go back to the question, just going back up here. All right, it's just rearranging your equation to get it x equals and then y equals. All right, and you can see I've kind of done that here. Oops, further down as well, sorry. It's getting a bit late. All right, so basically your solutions, x equals 4 over m plus 2 and y equals 2 times m plus 4 over m plus 2, but only when m is absolutely any other number except for -2 and 4. And when you think about it, if I was to substitute -2 into here, I would have a denominator that was 0, so undefined, which cannot happen. And then, yeah, the 4 gives us, was that our infinite solutions? So, yeah. All right, then there's another one, so you can have a go at doing that one. I think that one's a little bit easier. All right, and next video we'll go through these formulas, which probably we'll do in the next lesson anyway when I'm there, but looking forward to meeting you, and I hope, yeah, all is going well. Bye.